Welcome to the deep dive. Today we're digging into a really foundational text for anyone interested in materials.
Yeah, it's called Powder Metallurgy Processing. It was edited by Howard A. Kuhn and Alan Lawley, came out way back in 1978.
1978. And you might think, okay, that's a while ago, but honestly, the insights in here about techniques and how they analyzed powdered metals, they really laid the groundwork.
Oh, absolutely. And the list of contributors is, well, it's impressive. You've got people like John Talmadge on powder production, Robert Kuhner on compaction.
We've heard Haeckel on homogenization, Kuhn himself on deformation processing. It's a real who's who from that era of PM development.
It really captures a pivotal moment in the field.
Okay, so here's the plan. We're going to walk through this book chapter by chapter, basically give you a structured tour.
Yeah, the idea is to pull out the key concepts, the advancements they were focused on back then.
Right. So if you want a kind of quick way to grasp the core ideas in this specific influential book, this should give you that solid overview.
And going chapter by chapter makes sense.
Yeah.
Right? It follows the whole process, making the powder, pressing it, refining it.
All the way to thinking about, the economics of actually doing it on an industrial scale.
Exactly.
All right, let's dive in then. Chapter 1, Powder Production by Gas and Water Atomization of Liquid Metals. This one's by John A. Talmadge.
And right away, he makes it clear. The starting powder is everything.
Oh, yeah, he talks about its size, fine, coarse. Its shape roundish or more irregular, and obviously its composition.
Because all of that dictates how it's going to behave later. You can't make a good part if your starting powder isn't right.
He focuses on atomization, gas, and water atomization specifically. Still the big ones today.
And what's really neat is how he links the powder characteristics, the size, shape, structure, directly to the process parameters, the things you could actually control.
Like the properties of the molten metal itself?
Yeah, viscosity, how thick or runny it is, surface tension.
How it flows, the nozzle design, the jet geometry, he calls it, and then the atomizing fluid, the gas or water you're hitting it with.
He mentions nitrogen as the common gas they used, which is still true.
Yeah.
All these factors play together.
It's like baking, you said earlier. Flour quality, oven temp.
Exactly. It all matters for the final result.
And he doesn't just theorize. He talks about the actual experiments they ran, the setups, the procedures.
Right, and how they presented results,
Yeah.
often as particle size distribution plots.
Which sound technical, but they just show, how many particles you have of each different size. Are they all roughly the same, or is it a big mix?
And that distribution is super important for how well the powder packs together later. Uniformity helps.
Okay, then he gets into the how, the actual mechanisms.
Yeah.
How does that stream of liquid metal break up into tiny droplets?
He describes these different zones you can actually see in still photos from gas atomization. There's an upper zone, a central or apex zone.
And then a lower zone, like a shower of droplets. You can almost picture it.
And for gas atomization, he even lays out this 5-step sequence for how a flat sheet of the liquid metal breaks apart.
From starting as a sheet to forming ligaments, then breaking into droplets. Understanding that process helps you control it.
Definitely. And for the more science-minded listeners, he includes the underlying physics.
Fluid dynamics, heat transfer.
Yeah, how the fluids move, how heat gets pulled out of the droplets as they form and cool. He even includes some key equations.
So you can try and predict, say, the droplet diameter based on the process conditions. It's not just trial and error.
And he backs this up with experimental data. Tables and figures showing how changing things like gas pressure or water flow affects the particle size.
You increase the pressure, you generally get finer powder. Makes sense.
A key difference he highlights is particle shape. Gas atomization usually gives you more spherical particles, for most metals anyway.
Which tend to flow better, pack more easily.
Whereas water atomization often gives you more irregular, jagged shapes.
And that difference in shape really matters when you get to the next step, the compaction.
Big time. So yeah, Chapter 1 really sets the stage. Where does the powder come from? How can we control its basic properties, foundational stuff?
Okay, moving right along to Chapter 2. This one's Triaxial Stress State Compaction of Powders by Robert M. Kerner.
And Kerner starts by saying, look, there's no single best way to compact powder. It depends.
Right, he lists a bunch. Uniaxial pressing from one direction.
Isostatic pressure from all sides, like being deep underwater.
Powder extrusion, swaging, even explosive compacting. Sounds intense.
Yeah, but his focus here is on triaxial compaction. A bit less common, perhaps, but with some interesting properties.
So he breaks down the different stress states. Uniaxial is mainly force along one axis. Isostatic is uniform pressure. What makes triaxial different?
Triaxial allows for more complex stresses. You have confining pressure from the sides, like isostatic, but you can also apply an independent stress along another axis, often leading to shear stresses within the powder mass.
He uses diagrams in the book, which are apparently quite helpful. They show how pressure gets distributed in, say, a simple die.
Right, like pressing with a piston in a cylinder, versus the all-around pressure in isostatic compaction. The visuals make it clearer how the forces are acting.
And he connects triaxial compaction to tests used in soil mechanics, geotechnical engineering.
Exactly. Triaxial shear tests are standard for testing soil and rock strength under different pressures. Korner basically adapted that idea for metal powders. He even describes the lab setup, the triaxial compaction chamber.
So what's the advantage? Why go to this more complex method?
Well, Kerner's analysis shows how density changes, not just with the overall pressure, but crucially, with the amount of shear stress you apply during compaction.
Ah, so you have another control knob, essentially.
Precisely, and he presents data, specifically for iron powder, comparing density variations in parts made isostatically versus triaxially.
And the results?
The triaxial parts showed significantly more uniform density throughout, fewer gradients, fewer potential weak spots.
That makes sense. If the density isn't even, the properties won't be either.
Exactly. So the takeaway from Korner is that triaxial compaction, while maybe more complex to set up, can offer real benefits in density uniformity and potentially lead to stronger, more reliable parts.
Interesting. It opens up possibilities for applications where that consistency is absolutely critical.
Definitely. So pushing the performance limits.
All right. Chapter 3. Diffusional homogenization of compacted blends of powders. Richard W. Heckel? This sounds like alchemy. Getting different metals to mix.
Well, maybe a more scientific version of alchemy. It's about what happens after you've compacted a blend of different metal powders.
Okay, so you've pressed your mix together, but it's still just particles sitting next to each other.
Right. It's heterogeneous. Homogenization is the process, usually involving heat, where the atoms from the different powders actually diffuse. They move around and intermingle to form a uniform alloy at the microscopic level.
So you get the desired combined properties everywhere, not just patches of one metal next to patches of another.
Exactly. And Heckel discusses what influences this. Things like mechanical alloying, really smashing powders together first.
Infiltration, where you might flow a liquid metal into a porous structure, producing oxides.
And just the general homogenization, processing, the heat treatment, basically. Time and temperature are key.
He also looks at the different microstructures you might be dealing with. Simple binary systems, two-phase, three-phase.
Yeah, he uses schematic diagrams to show how diffusion happens in these different scenarios, how the atoms move across the boundaries between the original particles.
And then he brings in the mass kinetic models.
Right. Models to predict how fast this homogenization happens. They consider things like particle geometry. Are they flakes, cylinders, spheres?
Because shape affects the diffusion path length.
Exactly. And the initial composition, obviously. He presents equations that describe this interdiffusion and how the composition evens out over time.
But it's not just theory, right? He shows experimental proof.
Yes, absolutely. He discusses studies on systems like copper-nickel, nickel-tungsten. They use techniques like X-ray diffraction to track the alloying process.
And compared the results to what the models predicted.
And they generally lined up pretty well, showing the models were useful for understanding and predicting the process.
Does mechanically working the part, like forging it after sintering, affect this homogenization?
It can, yeah.
Yeah.
Heckel touches on that. Deformation can actually speed up diffusion sometimes by creating more pathways or defects for atoms to move through.
So it's a complex dance between temperature, time, particle characteristics, and even subsequent processing.
Very much so. The chapter really highlights that achieving a truly homogeneous alloy from a powder blend requires careful control and understanding, often using both modeling and experiments.
Got it. Okay, next up, Chapter 4, back to Howard A. Kuhn himself. Deformation processing of sintered powder metal materials.
So this picks up after compaction and sintering. Your powder particles are bonded, but the part probably isn't fully dense yet, and maybe not the final shape.
Right, so deformation processing is about squashing, forging, or otherwise working that sintered part.
But Kuhn points out a key difference from working with traditional wrought metals.
The porosity. You're starting with something that has tiny holes inside.
Exactly. And that initial porosity changes everything about how the material responds to being deformed.
So the chapter looks at how that porosity changes during deformation.
Yes, how it gets squeezed out or closed up, and crucially, how that densification impacts the mechanical properties.
More density generally means better strength, better ductility.
Generally, yes. He details various deformation techniques used for PM parts. Things like repressing, basically compacting it a second time.
Upsetting, squashing it shorter and fatter. Plane strain compression.
Compression where friction is a big factor. He even discusses designing forging processes for specific shapes, like discs.
And for each method, he explains the stresses involved, how the material flows to fill the die and close the pores. Uses diagrams and equations again.
Yeah, equations describing, for example, how density increases under different stress states.
And then he connects all this processing back to the final performance, the property-structure relationship.
Right. How does the way you forge the part affect its tensile strength, its impact resistance, its fatigue life, how it holds up under repeated stress?
He shows graphs, data, linking density and processing choices to these critical properties.
And he also discusses the negative impact of any remaining porosity or inclusions, little bits of unwanted stuff on those properties. Even small amounts can matter, especially for fatigue.
So the big message here is careful design.
Absolutely. Careful design of the initial cindered preform shape and precise control over the deformation process itself. That's how you get powder-forged parts with the properties you need for demanding applications.
Makes sense. It's about controlling that internal structure right down to the pores.
Precisely.
Okay, one more chapter to cover, and this one's a bit different. Chapter 6.
Yeah, this one takes a step back from the pure material science. It's economic risk analysis of a mini-clamp for production of steel strip from powder by Zecca, Dieter, and Thibodeau.
So shifting gears to the dollars and cents, or maybe dollars and risks.
Exactly. They're looking at the business case. If you wanted to set up a small factory, a mini plant to make steel strip using powder metallurgy, what are the economics? What are the risks?
They must talk about the costs involved, the initial investment.
Oh, yeah. Capital costs, buying the land, the building, the equipment. And then operating costs, raw materials, energy, labor, maintenance, all the day-to-day stuff.
But it's not just about adding up costs, right? They mention risk analysis.
Right, because the future is uncertain. How do you make big investment decisions when you don't know exactly what scrap prices will be next year, or energy costs, or even how quickly you can get the plant running efficiently?
So they identify all these sources of uncertainty.
And then they outlined a potential process for this PM steel strip plant, the technical side, to provide a basis for the economic analysis.
Okay, so how did they actually do the risk analysis?
This is the core of the chapter. They developed probability distributions for all those uncertain cost factors.
Meaning they didn't just guess one number for labor costs. They estimated the range of possibilities and how likely each outcome was.
Exactly. Like there's maybe a 50% chance labor costs will be X, a 25% chance they'll be a bit higher, a 25% chance a bit lower. They did that for capital costs, startup costs, scrap prices, power costs, taxes, everything.
Wow, that sounds pretty involved.
It is. And then they fed all those probability distributions into financial models, like a discounted cash flow analysis.
To see the range of potential financial outcomes, like the return on investment, considering all those uncertainties combined?
Precisely. They present the results as cumulative probability curves, graphs, showing the likelihood of achieving at least a certain rate of return, or the probability that costs will exceed a certain level.
So, based on all that, what did they conclude about making steel strip from powder?
Well, they discuss the results in the context of the time, weighing the potential against the calculated risks. It provides a really concrete economic assessment of that specific PM application.
It's a great reminder that even the coolest technology has to make economic sense to be widely adopted.
Absolutely. Innovation and economics always go hand in hand in the real world. This chapter provides a fascinating snapshot of that calculation for PM steel strip back in the late 70s.
Phew. Okay, we've really covered a lot of ground there, going through those key chapters of powder metallurgy processing.
We certainly have. From making the initial powder to pressing it, homogenizing it, deforming it, and even analyzing the economics of a full production line.
And even though it's from 1978, you can really see the foundational thinking that shaped so much of modern powder metallurgy. The core principles are still incredibly relevant.
Yeah, understanding atomization, compaction mechanisms, diffusion, densification, it's all still critical knowledge for anyone in materials or manufacturing today.
So as we wrap up this deep dive, maybe a final thought for you, our listeners, to mull over.
Considering everything we've discussed, the techniques for controlling powder properties, achieving density, creating alloys, the economic factors,
Sure.
where do you see the biggest potential for powder metallurgy today?
Yeah, what are the most promising applications now, building on this foundation? And looking forward, what new challenges do you think the field faces as it keeps evolving?
It's a dynamic field, always changing. Lots to think about.
Definitely. Well, we hope this exploration was useful. We certainly encourage you to keep digging into materials science and engineering. It's a fascinating world. Thanks for joining us on this deep dive.